Today's lesson is on solving quadratic inequalities. So yesterday we covered what a inequality is. We looked at how to write our answers in interval notation versus inequality notation. And then we also reminded ourselves about how to solve simple, compound, and absolute value inequalities. And now we're ready for the next set, which is our quadratic inequalities. Now, before I do that, I'd like you to recall one of the exponent properties that we talked about. And remember that when we take a root for a variable, when it exhibits that even, odd property, we have to use those absolute value bars. And remember, it's when the index is even and the variable's exponent is even inside the radical. When the exponent comes out as being odd, that's when we have to use our bars. All right. And so I'm going to use this when I do my solving. Example 1, solve each quadratic inequality and then write the answer in interval notation. So I have x squared is greater than 4. Well, I'm going to square root both sides here. All right, so here's what's going to be new. So now I'm going to do the absolute value of x is greater than 2. So what happens is when I do the left-handed side of my inequality, I know that that's my pattern where I have to use the absolute value bars. And then notice on the right-handed side, I did not put down the plus or minus 2. All right. So now I've got the absolute value of x is greater than 2. Well, we talked yesterday about if we have a greater than, that's the or type of compound inequality. So then I'm going to go ahead and set that up for myself. So I've got x is greater than 2 or x is less than negative 2. And that's my final answer here. If I were to put this on a number line, I'd have 2 here and negative 2 here. So I'd have a soft bracket on 2 with an arrow to the right, and then I'd have a soft bracket on negative 2 with an arrow to the left. So then in inequality notation, that would be negative infinity to negative 2, again, soft bracket on both. And then that u, remember, is to, it's in union with, so that joins together the solution sets. And then the second interval is 2 to infinity. So my final answer here is this part down here with the inequality notation. Now, last year you probably would have solved it a little bit differently. All right, so let's discuss, how did you do this last year in Algebra 2 trig? Well, when you had x squared is greater than 4, you solved these mainly graphically. So if I were to draw a little graph here, okay, I know that x squared is a parabola, right? Its vertex is at the origin, it's opening up. And then 4, I know, would be a horizontal line, so let me draw that in. All right, so where is x squared greater than 4? Well, obviously the left-handed side starts here, and then it's this piece, and then the right-handed side starts here, and it's that piece. And it's pretty easy to see that that's going to be at positive and negative 2. So that would be the solution if you did it graphically. But we're not really going to solve any of these graphically. The intersection points aren't necessarily that easy to, find. It's just for this particular problem, it's pretty easy to see that if you square positive and negative 2, obviously you get 4. So we're going to concentrate on the revising it into the equivalent absolute value and then solve like that. So when we're extracting the roots, that's going to be the method that we use. All right, let's look at number 2. So I've got quantity x minus 3 quantity squared is less than or equal to 81. So I'm going to square root both sides. So again, even, odd. So I have to do the absolute value of x minus 3 is less than or equal to 9. Now, notice that you have a less than equal to, so that's the and type of compound. All right, so now write out the equivalent compound. So I've got x minus 3 is less than or equal to 9, and I've got x minus 3 is greater than or equal to negative 9. All right, now we're going to go ahead and solve each one. So I get x is greater than or equal to negative 6, and x is less than or equal to 12, and then I merge them back together. So I get negative 6 is less than or equal to x, which is less than or equal to 12. My number line, all right, so here's 0, so let's say this is negative 6, so then 12 would be here. So then I'd have a hard bracket on negative 6, a hard bracket on 12, and then the region in between. So then in interval notation, it's a hard bracket for negative 6 and a hard bracket for 12, and that's the final answer here in interval notation. All right, moving on to number 3, I have x squared minus 4x minus 10 is greater than 2. So for this one, I'm going to start off by setting it greater than 0. So I've got x squared minus 4x minus 12 is greater than 0. And now notice that the left-handed side here can be factored. And so when I factor that, we'd have x minus 6, and then x plus 2 is greater than 0. Now, how do we solve a quadratic inequality like this? So the first two that I solved, I could extract the root. I could take the root of both sides. Well, here, that doesn't work out as nicely because I can't just square root the left-handed side here, all right? So in these cases, what we're going to do is generally we're going to factor them, and then what we have to do is we have to find the critical values. All right, so first, set it to 0, second, factor, okay, 3, find the critical values, and then you have to test the intervals. All right, now what are the critical values? The critical values are the zeros of the factors. All right, so in this case, my critical values are, I would have x is equal to 6, and then x is equal to negative 2. And so those are the zeros of my inequality. Now to test them, what I do is I make a number line, and I break up the number line at the critical values, in this case, negative 2 and 6. And so what this does then is this gives me 3 intervals. I have all of the numbers that are less than negative 2. I have all the numbers in between negative 2 and 6, and then I have all of the numbers bigger than 6. All right, now, in your mind, you just choose some arbitrary x value in each. So, for instance, I would choose maybe let x equal negative 3. All right. So then what I'm doing is I'm substituting negative 3 into my original inequality, the factored inequality. I'm substituting negative 3 into the factored inequality, and then I'm seeing if this is a true or false statement. So I'm putting negative 3 into each x, and so notice what's going to happen. The first factor is going to be a negative number, because you get negative 3 minus 6, and then my second number is also going to end up being a negative. Well, then the question becomes, is a negative times a negative greater than 0? And the answer is yes, because a negative number, regardless of what it is, times another negative number, the result is positive. And so that's going to be greater than 0. So what that means then is that any number in this region then is a solution. All right, so then I'm going to include that in my final answer. Now I'm going to move on to the next interval. I'm going to choose 0. I always like to choose 0 when possible. All right, so again, I'm going back to my inequality and I'm substituting 0 into each factor. So notice this time I would get a negative times a positive. Well, is that a negative times a positive is negative? Is a negative greater than 0? And the answer is no. So that means that this region from -2 to 6 then is a failure. It will not pass. Now we proceed to the last interval, 6. So in my mind, I'm letting x equal 7. One thing I forgot to mention is you never choose the critical values because those are going to make the answer, the product, turn to 0 every time. So you have to choose a number that's in the solution interval but not the critical value. All right, so now again, I'm substituting 7 into each factor. So notice that I would get a positive number times a positive number. Well, a positive times a positive is positive, and that is greater than 0. So that means then that any number in that interval is also going to check. All right, now how do I write my answer in interval notation? Well, because my inequality sign is greater than, that means that I need to use soft brackets. So I need a soft bracket on -2 going to negative infinity, and then I need a soft bracket on +6 going to positive infinity. So my final answer here is negative infinity to -2 in union with +6 to positive infinity. And that's the final answer then. All right, let's try the next one, number 4. It's pretty similar to number 3. First, set the inequality to 0. So I've got x squared minus 2x minus 3 is greater than or equal to 0. Factor the left-handed side, in this case, x minus 3, x plus 1. Now, find your critical values. My critical values are going to be x is equal to 3 and x is equal to -1. Now I'm going to test my intervals. So I've got -1 here and I've got 3 here. All right, so in my mind, the first number I'm going to test is let x equal -2. I'm testing in my factored inequality here. All right, so when I substitute -2 into that, notice that I get a negative times a negative. Is that going to be greater than or equal to 0? And the answer is yes. So this is a true statement, right? A positive is greater than or equal to 0. So that means that this region is going to be a solution, any number in that. Okay, next one I'm going to test is let x equal 0. Again, I'm testing in my highlighted inequality there. So I've got 0 minus 3 is a negative, 0 plus 1 is a positive. Is a negative times a positive greater than or equal to 0? And that is no, that's a false. So that means that this is not a solution, any number in that interval. And then my last one, I'm going to choose 4 in my mind. So then when I substitute 4 into my inequality, notice I get a positive times a positive. Is that greater than or equal to 0? And again, that's true. So that means that any number in that interval is also a solution. Now notice that you have a hard bracket because you've got greater than or equal to. So that means I need a hard bracket on -1 and I need a hard bracket on 3. So my final answer here is negative infinity to -1, hard bracket on -1, soft on infinity. Remember, infinity is never hard. And then in union with 3, so again, hard on 3, and then positive infinity, and then a soft bracket on infinity. All right, number 5, you actually can choose which technique you want to use, if you want to extract the root or if you want to set it to 0, and I'm going to show you both ways. Okay, so method number 1, I'm going to continue setting to 0 just like I did before. So I've got x squared minus 6x minus 7 is less than 0. And then notice that the left-handed side would factor then into x minus 7 and x plus 1. And then my critical values here would be x is equal to 7 and x is equal to -1, and then I'm going to test the intervals. All right, so that's the same technique that I just did on 3 and 4. Now look at what happens if I wanted to solve it using the method that I used on 1 and 2. So notice that I'm, again, starting off with x squared minus 6x plus 9 is less than 16. Well, the left-handed side is one of my special factoring patterns, and this is x minus 3 quantity squared is less than 16. So because the left-handed side is a perfect square trinomial, it's more efficient to factor that and then extract the root. And I didn't do this on any of the other ones because they didn't exhibit that behavior. So then notice that my left-handed side would be the absolute value of x minus 3 is less than 4. Again, less than is an and type compound inequality. So then I would have x minus 3 is less than 4 and x minus 3, so flip the sign and change, or flip the inequality and change the sign, and x minus 3 is greater than -4. So then I get x is greater than -1 and x is less than 7, and then just merge them back together. So I get -1 is less than x, which is less than 7, and then in interval notation that would be -1 to 7, and again a soft bracket on both. So that would be the final answer here. So when you can take the root, when you can extract the root and then write the equivalent compound inequality, that's generally faster than factoring and then testing all the intervals. But either technique is okay. They're both correct, and it's just kind of personal preference. The second way, of course, is only going to work on certain problems, and you've got to have a quadratic that is a perfect square for this to work out nicely. So just kind of keep that in mind. All right, that's going to do it for the lesson today on quadratic inequalities. And make sure that in your homework packet you do the quadratic inequality assignment.